the game of Go, if you're not familiar with, is something that is a board game that is much more complicated than chess. If chess is a board of 9 by 9 or 8 by 8, in Go it's 16 by 16, and the number of options is substantially larger. So this is a very complicated task for a computer, and also for human. And in 2016, they succeeded to show that this program beats the world champion. So it was in the headlines that the computer is better than the world champion. And later on, they played against the top 10 players. And in the beginning, it was 6-4 to the computer. Later on, they improved it to 10-0 to the computer. So the headline said that the computer is better than a human being. And other examples of how AI is going to, destroy the humanity and do a lot of things. But they, of course, ignored a few things. One is that this program can only perform the task of playing Go, right? Unlike the world champion, that is maybe the best person in the world in playing Go, but he can drive and talk and make many different decisions that are unrelated to the game of Go. So that's one big difference between a computer program and AI. But the second thing that the media ignored is the hardware. And when we talk about the hardware, in order to play a game of Go in AlphaGo, they had to use more than 2,000 processors, both CPUs and GPUs, just in order to play against the world champion. And the electric bill per game was more than $3,000 for a single game. And of course, the world champion, what he had to do is maybe to take a bite from a sandwich in order to have this energy. So definitely, even if a computer can be today better than a human being in specific tasks, even tasks that we considered as human intelligence tasks, the hardware is not efficient enough. And we saw also yesterday and today a lot of other different examples to that. And it's true that the gap is maybe we are lowering down the gap, but it's still orders of magnitude less efficient in terms of energy efficiency. Yes?
What does it mean 2,000 per game? It's just forward pass? I mean, it's not learning.
No, it's not learning. It's after the learning. Of course, this
it's much more.
So the learning must be infinite.
If it's infinite, I don't know how they exactly implemented the AlphaGo and if it's retrained, but it's playing games. They trained it with thousands of games previously, and then they made the inference. So the game is only inference.
It would mean millions of dollars to train.
Yes, the training is millions of dollars and takes a lot of time, right? It's probably a month of training. And of course, they have new versions, and the new versions are better with training. And by the way, the newer versions are not based on CPUs and GPUs, but on TPUs, like on dedicated hardware, and I will go there. OK, so the main reason for the inefficiency is the way that we build computers. OK, we are building computers for 80 years with the same structure of the von Neumann architecture. Computers from the 40s and computers from that are built today basically are looking the same. Okay, I teach an undergraduate course in the first year called Digital Systems and Introduction to Computers. And actually, this is the same course that was taught in the 50s. Okay, so we are teaching RISC-V processors that are like basically maybe the most advanced processors or the newest processors that are widely used today. But actually, the course material hasn't changed for 60, 70 years. Okay, we only changed the syntax. We knew that the course 3 years ago to move to RISC-V, and actually only we changed was the order of the bits. And slightly the instruction set. The structure of the computer hasn't changed. And the separation between the processing and the memory, this is the root cause for this inefficiency. First, in terms of performance, most of the time that we spend in programs goes to the data movement between memory and processing. In some applications, it can go to 90% of the time is for data to move from the memory to the CPU. And when we talk about energy, this is even more severe. Actually, Damien showed yesterday the exact same numbers. They are taken from a paper that we had when I was at Stanford, that we took different operations and we evaluated them. Then it was on 45 nanometer, but for more advanced technology nodes, it's exactly the same trend. So the numbers are different, but the ratio is quite similar. And you can see that taking data, one single number from the memory, is more than 3,000 times more energy than the processing itself. So we want, for example, to add two numbers. We need to spend 10,000 times more energy than the addition itself, just because we need to move the data. And actually, this is true for general computing, but it's even more severe when we talk about deep neural networks, for example, because in deep neural networks, we have a lot of data, like millions of, like this graph shows different known models for ImageNet. And you can see the size of the circle means how many weights we have in the model. So it goes into the millions, and actually the trend is just to increase it to billions. And the weights mean that we need a lot of memory, and we can't put it on die. We can't put all the memory close to the processors. And the x-axis here shows how many multiply accumulate operations we need. It goes into billions, so it means that we need to calculate a lot of operations, but also we need a lot of memory. So this is a big problem. And if we look in the application level, so those are numbers for the energy consumption for different, for two examples. One is AlexNet and the other one is LSTM, but it's true for all the other models as well. And you can see that more than 85% of the energy goes into the memory operations and not for the computation itself. Just because we need to bring the weights or to bring the inputs in order to perform the computation. Okay, so that's a bad place to start with, right? Which means that we have a lot to do, which is good for researchers. And of course, also for industry, because those applications are widely used. And the first thing that people are doing is to use commodity hardware, right? Mostly GPUs. And GPUs have shown to be much better than the standard CPUs that were used in the beginning. In addition to that, there is dedicated software, different platforms that should be more efficient to describe the different operations that are required. And also, mostly for inference, there is dedicated hardware, mostly ASIC, but also FPGAs. And this is, of course, not enough because of the big gap that exists. So in the last couple of years, we are seeing new approaches. One is to improve the GPUs. So if you ask, for example, NVIDIA, and then I had this discussion with Bill Daly, the chief scientist of NVIDIA, and he said GPUs will solve everything. We don't need dedicated hardware. GPUs can do everything. And actually, what they're doing is that they're putting dedicated hardware inside GPUs. So for example, I think 2 years ago, they added tensor cores inside their GPUs, which are basically accelerating small matrix multiplications. But I even had this discussion this week with someone in NVIDIA. He said, no, we are not using accelerators. And then I asked him about this and said, OK, you can call it an accelerator. Okay? But like in their terminology, they like to say that everything is inside the GPU. But their GPUs are now enormous, right? They have the DRAM on the same package with the GPU. And they have a lot of memory close to the GPU. So those are like every GPU consumes hundreds of watts. And they are very expensive. And usually you need multiple GPUs in order to perform those tasks. But that's one approach. And the other approach is to have dedicated hardware. And when I say dedicated hardware, it can go to conventional hardware, like Google are building the TPUs. They already have the 4th version of a TPU, started as an inference machine. Now they're performing training with TPUs, and they come in different sizes. And it can also go to smaller devices that are going mostly for the edge. And we see them like in mobile phones. Today, in every mobile phone, we have different accelerators that are dedicated to perform neural networks. And here comes, of course, neuromorphic computing. So I don't need to say again the motivation about the brain and how the brain is efficient and gives us at least inspiration for having the hardware. And I want to say just one thing, a general thing about neuromorphic computing, that actually when people are saying neuromorphic computing, they mean many different things. Okay, it can be software. Some people, when they describe things that are bio-inspired, they call it neuromorphic computing. It can be digital hardware. For example, Intel has Lohihi. It's pure digital based on transistors, but it's a neuromorphic chip. And of course, analog, that was mentioned a lot over the last couple of days. And also in terms of system, for example, in Manchester, they have Spinnaker, which is multi-core supercomputer that mimics or is a brain-inspired machine, but it's multi-core, many different processors that communicates between them. So they are all called neuromorphic. And then, by the way, I mentioned NVIDIA. If we'll ask NVIDIA, they'll say GPUs are neuromorphic because a lot of parallelism, they mimic the brain. Okay. So when we say neuromorphic, it's becoming like something very large. I will focus mostly on analog, maybe a bit digital in this talk, but other people may say that neuromorphic computing is something else or something more broader. And also, actually, neuromorphic, usually when we think about neuromorphic computing, we're thinking about Carver Mead from the 80s as the first neuromorphic computing or first neuromorphic circuits. But actually, it started much earlier. So does anyone knows what's this? So that's at least the first known neuromorphic circuit. It's called SNARC. It's from 1951. It was built by Marvin Minsky. He got the Turing Award in 1968. And SNARC is an acronym name for Stochastic Neural Analog Reinforcement Calculator. He had 40 neurons. It's pure analog. They changed they used the potentiometers to change conductance. He did it as a PhD student, as a side project. And actually, it's not well documented. So there are a few pictures, but no one really knows how it was completely built. He did it. And we did a lot of work on AI afterwards, but mostly from the algorithmic side. OK. So I'm going to focus on neuromorphic computing with emerging technologies. So I would say that what we are doing is in the domain of what Alice talked about and Damien. We are using emerging technologies in order to build neuromorphic computing. And basically, we are exploring other maybe different circuits, but our motivation and the background is quite similar. We are not working on a specific technology. I will explain a few technologies that we are working on. Basically, we're saying that we're working with memristors. Memristors, Damien talked about that yesterday. For us, at least, memristors are a family of many different non-volatile memories that change their resistance, or usually when we talk about neuromorphic computing, we say conductance, which is basically the same thing, right? But it's better to look on conductance because then high conductance and low conductance is proportional to the weight. And in resistance, it's the other way around. So we are looking on resistive RAM and also about spintronics, and also for phase change memories, and also on flash that I will elaborate a bit later. So memristors, just in short, it's a theoretical concept. So we can talk for hours just about the philosophy behind it and whether like the devices that we're using are really memristors. But the theory came from the 70s, and the emerging memory technologies that are used today are not really obeying to the theory, but it's nice to think about that. And by the way, from the first memristor paper, in the first memristor paper from 1971, what Shua did was also to talk about ion channels and models for neurons using memristors. So again, the connection between memristors and brain-inspired computing is also not new and actually came from back then. A memristor basically is a resistor that changes its resistance or conductance. Different technologies have different behavior. Yesterday, Wolfram talked about phase change memory, and he showed the different pulses. In spintronics, for example, if it's a spin torque transfer, then you have only two resistances, and the current changes the direction of the magnetic field. But in most technologies, when we talk about the changing of the resistance, it's by the direction of the current and an analog or continuous resistance. So for example, if current goes into one direction, then the resistance will drop. And you can see this in this graph that in slightly increasing the voltage will substantially increase the current because the resistance is also going down until it will reach some physical limitation that we call the low resistive state. And if the current will go to the other direction, then the resistance will increase. And again, there is some physical limitation which gives us the highest resistance, the high resistive state. And if we won't apply any current or voltage, then the resistance remains unchanged. So it's a memory device. It remembers its state through resistance. And we can use the different values of the resistance to store weights or to store information in general. That's why they are, firstly are used for memories, because we can store information through resistance. And it can be multi-level. We can think about different values of resistance as different numbers, or it can be binary, like in a magnetic tunnel junction in spintronics, where we say, okay, we have only two states, two stable states, 0 and 1, or high and low resistance. And the way that we perform the computation for neural networks is using mostly the matrix vector multiplication ability of them. And for example, for inference, we can cascade together different arrays. Each array performs efficiently the matrix vector multiplication. And we will store the weights in the memristors. So the memristors can perform both the data storage, because the weights are stored inside the memristor, but they can also perform the computation. So unlike in a standard von Neumann machine, where there is a separation between the data storage and the data computation, now it's all done using the same physical devices, or at least they participate in the computation, because using only the memristors is not enough. And we are using the analog storage capability, the fact that we have multiple resistance levels, in order to make the arrays more dense, basically. But if we are using only binary devices or less resistance levels, then we need more arrays. And usually what we will do is to use a few steps, because we won't be able to do it in one step. So basically, the idea is to store the weights inside the array, and the conductance represents the weight values. And the way that we will perform the computation is by applying voltages as the activations, using conductance as the weights, and accumulate currents in order to get a result. So the way that we will do it is through accumulation of currents. So we're using Kirchhoff's law, basically, to perform in one step or in multiple steps. If we are not able to store the entire weight in a single device, then we will need a few steps. But accumulation of currents will give us the ability to perform efficient matrix vector multiplication. And with that, different technologies gives us different abilities. For example, here you can see results for phase change memory. So you can see here multiple weights that, multiple resistance values that represent different values that can be stored as the weight. And through a few steps, we can program them to the desired value. Technology that we are working with a lot is actually flash technology. So you can see here a transistor, or a floating gate transistor, actually two transistors, because they are used, one transistor is used for read and one for the write operation, but they are connected together. They have the joint floating gate and the joint drain. So this is actually one transistor that is built from two transistors, but it can also be built from a single transistor, but then one of the operations will be less efficient, either read or write. And those are flash technologies that are manufactured in Tower Semiconductor, completely commercial. They exist in 180 nanometer, 130 nanometer, and actually even in 65 nanometer, and maybe even more advanced nodes. So it's a completely commercial flash technology. But we demonstrated that we can transfer them into memristors because the gate is completely floating. So we have here a joint source. If we shorten the source together, then we have a two-terminal device. It's a resistor. And when we work in the sub-threshold region of this transistor, then we are able to have multiple resistance values. You can see here in this graph the different colors. Actually, every color is a different resistance level. And we successfully demonstrated 65 distinguishable resistance values. So we can store here quite a lot of information in terms of weights. If we can tolerate more noise, then we can even have hundreds of resistance levels. So this is actually a very nice device for neuromorphic computing. And it's pure commercial. So it exists. It's compatible with CMOS. So we can tape out with that. We demonstrated experimentally that it's really distinguishable. And we also developed device models for them. So we have also all the CAD tools that are needed in order to have circuit design and to tape out them. And I will later on show something that we taped out and demonstrated all neural network. So this is one technology that is available to everyone. And it's relatively low power, unlike most of the flash technologies. And we like to use it to demonstrate some of our ideas. But any other technology has its own pros and cons. And we saw in this workshop a few other technologies as well. And with this concept, we can build different neural networks. We can think about them both as analog or digital, and we can mix between them. We can use the activations as continuous voltages or as digital voltages like 0 and 1. The same we can do for the weights. We can think about the weights as digital or pure analog, and we can mix between them. And we can build from that different accelerators for AI. The first architectural work that was done by a group from University of Utah and HP Labs in a paper called ISAAC. And what they did was to take this concept of performing matrix vector multiplication using memristors in order to build an accelerator for DNN. And what they did was to build it with many different tiles. Every tile has multiple units that they called in situ multiply accumulate. So they have 8 of those. And each one of them has a few crossbars and separated analog to digital and digital to analog converters. So the conversion between analog to digital is done in this hierarchy, but not per array. But they have a bus that transfer the analog information and then they convert. And even for them, the main bottleneck was the conversion between analog to digital. And actually, they showed that if you want to improve the precision by 1 bit, it's doubling the area and the power of the ADCs. So basically, it doesn't scale well. So after them, many works have demonstrated that the conversion between analog to digital is the main bottleneck on those architectures. And most of the power and area goes to the conversion and not for the arrays, which are extremely dense because memristors are extremely dense and extremely efficient because in one cycle or a few constant cycles, we can perform the the matrix vector multiplication. But since then, I think that if you look on all like the accelerators that are based on memristors for AI, it's all goes to something similar. So they're all like improvements of ISAAC with the same concept. And they use like the weights that are stored in the memristors, so the weights are stationary. The activations are moves between the tiles, so they can build multiple layers. We took a different approach. Of course, this is good for at least this meant to be used for data centers, for large neural networks, to perform a lot of computation. One thing that we have done was to take a different approach and to think about an inference engine for the edge, which means that we want to do it for small neural networks and not using multiple tiles with a lot of memory and a lot of units, but something small. So in a paper that we published last year that is called multi-pulply, what we did was to take the PULP platform. The PULP platform is a platform based on RISC-V that is used for microcontrollers, for edge devices. And we added to it a small engine, a small accelerator that is based on an array of memristors. So this small array, and we explore different sizes from 64 by 64 up to 256 by 256. This is only a single array or two arrays that are used. So of course, it means that we cannot store all the weights in this accelerator. So we need also to move the weights. But we develop algorithms to reuse as much as we can the weights. So we try to minimize the amount of data movement of the weights. But of course, we need to move the weights. Unlike ISAAC, for example, that all the weights are stored in the memristors, but there is a lot of computation that is done. And you can see here some numbers. So we can do it with a few milliwatts. And of course, this may be useful only for small neural networks and not for neural networks that requires a lot of weights and a lot of computation. So that's one approach, to build accelerators for the edge with limited size of arrays and a small number of arrays. And it comes with the cost of moving the weights as well. OK, so that's about inference. Let's talk about training. So for training, what we actually do is basically update the weights, or updating the conductance, or the data that is stored inside the memristors. So if we want to do it naively, what we need to do is to do the backpropagation, and we need to calculate, for example, the gradients and update each memristor. So we need to support the a precise programming of the memristors according to the number of levels that they can store. And usually, if we are doing that, it means that the update of all the memristors can take a lot of time because we need to go one row by the other, if we can even program all the rows, and perform precise programming of each one of them. We thought about a different approach in order to update all the weights simultaneously, to do it in parallel. So in order to do that, in order to perform everything using the same circuits that are used also for the feed forward, what we did is first to support the backpropagation. Supporting the backpropagation is quite easy because the backpropagation itself is just another matrix vector multiplication, but with a transpose matrix. But since the crossbar structure is symmetric, then we can perform it. We change the outputs into inputs, and what was the activations now is the output. So we need to double the amount of peripheral circuits, but it's using the same pattern of the way that we perform matrix vector multiplication. The more complicated thing is to make the weight updates, and to update the weights simultaneously on multiple rows. And we cannot do that with the crossbar structure. Okay? The crossbar structure doesn't support the update itself. So what we did was to extend or to change the cell structure, and we added 2 transistors per each memristor. And those transistors basically perform the gradient descent operation by performing basically multiplication of the input and the error. So we need to calculate the error, and then we need to backpropagate it. And then for every cell, we have its own multiplication of the error and the input. And the way that we are doing it by transferring voltage into time. So we apply a specific amount of time for every device according to the amount of errors that it has. If it has longer error, then the pulse will be longer, and vice versa. And the same goes to the, if the error is negative or positive, then it will go through a different transistor. So negative errors will go through here, and positive errors will go through here. And basically, because we use the N and P transistors, so one of them will be open when we have a negative voltage, and the other when we have a positive voltage. So that's how we basically perform the multiplication. So all rows will get the same error. All columns will get the same input, and each cross point is a different pair of input and error. So it will perform basically the desired multiplication. So at the cost of adding 2 transistors per cell, so increasing the area, we are able to perform gradient descent training simultaneously. Okay, so this is for the basic stochastic gradient descent. And then we thought on how we can perform more complicated training rules. For example, stochastic gradient descent, but with momentum. And when we talk about gradient descent with momentum, basically a momentum is remembering the history of the previous updates. Think about that as if a gradient descent is going in the hill to the lowest location, and every time we have a step, then with momentum we have also the velocity that depends on what happens before. So we have a ball that goes down the hill, but there is a velocity that depends on what happened previously. And this is basically what gradient descent, stochastic gradient descent with momentum is. So we need somehow to remember all the previous updates and to consider them when we perform the next update. And again, we want to do it in hardware within the same array. Okay, so mathematically, this is how it looks. So this is the original stochastic gradient descent. And in addition, we need to remember all the previous updates. Each update has some parameter that is smaller if it was older. Like previous updates get a lower weight. And we need to accumulate all of them, to summarize all of them in order to consider that. So this is the momentum. And we want to support that as well, because this is something that we saw previously on how we are doing it. So in order to do that, we took two approaches. One was to have a limited history. So we say, okay, although that in the original algorithm, we need to store all of the history of the updates, but this is hard in terms of hardware. It will require a lot of memory. What we will do is we will decide on a parameter that is the amount of history. Let's say that we store only the last 10 updates. So we will store it. We will have a fixed size memory that will be used for the history. And this will be an approximate of the original algorithm. And the second approach was to have another memristor that will store internally the specific updates of this weight. And this will be used also as an additional analog memory. And this is supposed to be closer to the original algorithm. But it will require changing the synapse cell as well. So for the limited history approach, what we did was to have an SRAM close to the memristive array. And this SRAM is relatively small because we store only a fixed size history. And every time we need to add from this SRAM, we need to add the momentum from the data that is stored in the SRAM. So basically, if, for example, the history is only remembering the last update, so age is the parameter of how many steps back we are storing. So if age equals to 1, it means that in the first step, we will calculate the updates based on the momentum. So this is the multiplications that we are doing with the previous update. And then we'll perform the standard stochastic gradient descent. So we need 2 steps. And again, if age is 10, then it means that we need 11 steps. And actually, the results were surprisingly good. So you can see here, this is the accuracy for stochastic gradient descent. This is the accuracy for stochastic gradient descent with momentum with unlimited history, like the original algorithm. So you can see that, of course, the accuracy is better. And with limited history, you can see that we get still much better results than the original algorithm. There is a degradation compared to the original algorithm, but it's much less severe than. So it's much improved compared to the stochastic gradient descent. And you can see that it's for a relatively small history, 10 or 20 updates. Remembering 10 or 20 updates is enough to get reasonable results. OK, so that's one approach. The second approach was to store it internally inside the array. So this is the original circuit that supports stochastic gradient descent. What we added is an additional memristor that stores the history. And we have some additional circuitry to perform the calculation of the momentum. So this is more than doubling the area of the array. But it is more accurate because we store the entire history. And when we talk about how much time it takes us to converge compared to software, we see that it doesn't really matter what approach we take. They're both very similar to the software, to the original algorithm. So you can see here for different iterations what will be the accuracy. And you can see that you can't really distinguish between the original algorithm and the hardware solutions. So in terms of accuracy, we can get good accuracy and similar behavior to the original algorithm. In terms of speed, we compared our work to GPUs. And actually, we saw that it's extremely faster compared to GPUs. You can see that even the limited history that requires data movement between an SRAM to the memristors is 2 orders of magnitude faster than a GPU. And when we talk about the internal solution, then it's even faster, 3 times faster than the limited history. OK, so that's one approach for performing stochastic gradient descent or even an extended one. A different approach is to reduce the precision. OK, and I think Alice talked about binary neural networks, or was asked about that. And that's something that we are also looking at, mostly for the training. So usually, like the standard convention is that training should be done with like 32 bits or high precision, and inference can be with lower precision. One interesting thing is to look on training with lower precision. And we took it to the extreme to binary and ternary neural networks. So ternary means that it has -1, 0, and 1 as the values. And when I say binarized neural networks, unlike most of the binarized neural networks for training that is used, that there is full precision somewhere hidden, I'm talking about real binary or ternary, which means that everything is done with 2 or 3 values. So when we want to train with that, basically the algorithm, you can't just update the weight in every step. Because if you update the weights in every step, then we'll move from -1 to 1 all the time, and we won't converge. So basically, in order to do that, what we need is some probability. So basically, every step computes a probability to switch. And on average, it will converge to one of the values, -1 or 1. So this is basically the algorithm. You can see here the calculation of the probability. And in order to support that in hardware, what we did was to move to spintronics. So the switching in magnetic tunnel junctions is stochastic. And what we did is to calculate the probability in hardware. And the probability is represented as the pulse that is applied, or the current that is applied to the magnetic tunnel junction. So you can see here, it's a similar circuit to the circuit for stochastic gradient descent that I showed earlier. But now we are applying a specific pulse that is proportional to the probability. So we implement the algorithm using hardware. So we can have training of binarized or ternary neural networks in hardware using stochastic training. Okay, how much time do I have?
I would say 10 minutes.
Okay, good. Okay, another thing that we are looking at in terms of neuromorphic computing is to build data converters. So data converters are used in neuromorphic computing, but actually they are used everywhere because the world is analog, but computers are mostly digital. So we need to convert all the time. Every computing device that is connected to the world, either through communication or sensors or whatever, requires data converters. And if we look on data converters today, actually they are very different one from the other, because there is a trade-off between accuracy, the amount of bits that can be represented when we are, for example, converting from analog to digital, the amount of bits that represent the digital value, from between speed, how fast they can do it, or what is the sampling rate, and between the power. And there is no ADC today that is both fast, accurate, and low power. So usually, for different applications, we have, like, if we want to do it for medical devices that should be very accurate, then they will be relatively slow or will consume high power, and vice versa. Okay, so different. So if you look, for example, in Texas Instruments, that are the world-leading providers of ADCs, they have more than 1,000 different ADCs in their catalog, and each one of them, or not each one of them, but they have different architectures for different ADCs, sigma, delta, and SAR, and different architectures. Okay, so what we thought that will be a nice thing to do is to build a neuromorphic data converter. This neuromorphic data converter is basically a neural network, because if you think about that, analog to digital conversion is a machine learning task. You get an input, some analog voltage, and you need to categorize it into its class, right? It's either 0, 0, 0, 1, or 1, 0, or 1, 1. So it's very similar to take an image and classify if it's a cat or a dog, and to take an analog voltage or classify it if it's 0, 0, or 0, 1. Conceptually it's the same, and actually it's even much simpler task than image classification, for example, because you have only one dimension for the input and only very few classes for the output. So that's the motivation. So this is the circuit for a 4-bit ADC, and you can see here how in red this is that's like the ideal output, and in blue that's the output that we get from the circuit. So in the beginning it's very, very inaccurate, but after a few thousands of samples, it gets the perfect output. And it's not surprising that it achieves the perfect output, again, because it's a simple classification task. And the advantage of such a data converter is that it's general purpose, because if we want better accuracy, we can train it to be more accurate. ADCs usually suffer from poor performance when we have process variations, for example. Here the training compensates on process variation, because it will be trained, and it doesn't need to know how the transistors behave or how the memristors behave. At the end, we'll give it enough samples that it will achieve the perfect match. So it can compensate on process variation. It can fit different applications. So it's a great ADC. And you can see here, all the dots in red are different ADCs that were published in ISAAC mostly, which is a chip conference. And in star, you can see this ADC in terms of figure of merit. Figure of merit is a combination of accuracy, power, and speed, sampling rate. Okay, so it's most like, if you take it together, it's the energy per a single conversion. So lower is better because it's lower energy. And you can see that even though that we used a relatively old technology node, it still gets 1 to 2 orders of magnitude better figure of merit. And those data converters are just, I think, the first step, because this allows us a larger concept, which is compute in analog and get the result in digital. So we can think about, for example, computing in sensors. So we get analog signals, build a neural network that is working in analog, and throughout the computation, not only that we perform the tasks that we want, but also we get a digital result. So we need to convert. Today, what we usually done is that we first convert from analog to digital, then sending it to a DSP, some processors that perform things in digital, and then only then we get a result. Now we can reduce the amount of data that is required in digital and perform some of the tasks in the neuromorphic computing. So that's about data converters. And the last thing that I want to talk about is also related to reducing the precision, because data conversions, as I said, are the bottleneck. So we also looked on different neural network topologies, for example, deep belief networks. So the advantage of deep belief networks is that we're using neurons that are binary, and the training is done using a digital counter, because we accumulate the amount of errors that we have, and then when we reach a certain threshold, then we update the weights. And so this is an example of the topology of a deep belief network. And we explored it with different technologies. And you can see here we took a resistive RAM, and we took a phase change memory, and the CB-RAM. And we showed that we can, using this structure, we can achieve high accuracy when we consider all the physical elements of that. And we can reach high accuracy, but the hardware that is required is much simpler than using it with a stochastic gradient descent training, for example, because we use simple arrays and only a digital counter for the training. So supporting the training here is extremely low cost compared to the circuits that I showed earlier for stochastic gradient descent. So this was done exploring different technologies. And next week, we will have a paper that will be published in Nature Electronics this Monday that is based on the Y-Flash. So we taped out with a tower a chip with arrays of Y-Flash memristors. And you can see here that you can see the accuracy that we achieve with this chip compared to deep neural networks with other technologies. And it's close enough. It's very close in terms of accuracy, although it's much, much simpler in terms of the hardware that is required. And with that, I want to conclude that basically I think that neuromorphic computing gives us a lot of inspiration from the brain. As you saw, it's very different than brain-inspired models, but it's also very different than von Neumann and from conventional computers. So this inspiration, I think, gives us a lot of good ideas for things. Different technologies gives us also different capabilities. The advantage of spintronics, for example, gives us the probability that can be performed for different algorithms. Other technologies give us the almost analog nature for the computation. And I think that one field that is very interesting and still not explored enough is going to the edge and perform training at the edge. That requires, unlike training in data centers, it requires lower precision, lower power, less samples, because we cannot have a lot of information, a lot of data that is stored at the edge. So we need to think how to train without having a lot of samples. So I think that's something that will be developed a lot in the next few years, and there is a lot to do there. And with that, I want to thank you again. Thanks.
You have any questions?
belief networks, you do need examples. That's true. Yes, that's not. I don't think the deep belief networks is a good example for reducing the amount of samples, but there are other approaches for. Forgot the name of that. You basically almost don't have any. I remember the name after that. It's something that we started to look at. You basically use a very few examples. You do need some samples, but very few, and most of the training is done unsupervised. But the few examples that you get, fine-tune your results.
Few samples.
Yeah, exactly.